Matrix, arithmetic, and operations. With row operations, we can add or subtract multiples of a row to another row, we can multiply a row by a constant, or interchange pairs of rows. Row operations is about doing stuff to the rows of a matrix, whereas everything else that we'll be talking about in this lesson is about doing stuff to the entire matrix. Find the trace of a matrix by adding up all of the elements along the main diagonal. This means that we can only get the trace of a square matrix because a non-square matrix does not have a main diagonal. Let's say we want to find the trace of matrix A. We add the elements along the main diagonal, 1 plus 4 is 5. For matrix B, the trace is 1 plus 0 plus negative 3, it's negative 2. The trace of matrix C does not exist, D and E, because C is not a square matrix. To transpose a matrix, we flip the elements across the main diagonal. Another way of thinking about the transpose in a case that the matrix does not have a main diagonal would be to turn rows into columns and columns into rows. Consequently, the dimensions of the matrix are also interchanged. Also, notice the property that the transpose of a matrix, we get back the original matrix. Think of it as turning rows and columns of the original matrix into columns and rows of the transpose, and the columns and rows of the transpose again back into the rows and columns, which match up with the original matrix. Here we're asked to find the transpose of the matrices and their dimensions. We're given matrix A and we have to find the transpose. Matrix A is square, so the entries along the main diagonal, the 0 and 2, stays as is, but then the 5 and the negative 4, they flip across that main diagonal. Since A is a square matrix, the dimensions doesn't change between the original matrix and the transpose. The original matrix is 2 by 2, the transpose is also 2 by 2. B has the first column as negative 5, 5, and 3. The transpose of B is going to turn that first column into the first row, negative 5, 5, and 3. The second column in B, 1, 6, negative 7, becomes the second row in B transpose, 1, 6, negative 7. Now look closely, this is where the dimensions do change because B is not square. B has 3 rows and 2 columns. It is 3 by 2. But B transpose now has 2 rows and 3 columns, 2 by 3. As a side note, we don't need to go column first and then row. We can go row and then column. We're given C transpose, but when we transpose a transpose, we actually get back the original matrix, C. The first column, EI theta, becomes the first row, EI theta. The second column, pi phi x, becomes the second row, pi phi x. C transpose has 3 rows and 2 columns. C transpose, or just matrix C, has 2 rows and 3 columns. D is a row vector, 1, 2, 3, 4, going horizontally. The transpose just turns that row into a column. D transpose is 1, 2, 3, 4 vertically. D is 1 by 4. D has 1 row and 4 columns. D transpose has 4 rows and 1 column. E is a column vector. E transpose becomes a row vector. The dimensions of E is 5 rows by 1 column, and the dimensions of E transpose is 1 row by 5 columns. Matrix F is kind of interesting. Matrix F is diagonal. There are non-zero entries along the main diagonal, and zeros everywhere else. When we take the transpose of F transpose, we get back the original matrix F. The entries along the main diagonal stay put. Everything else flips across the main diagonal, but everything else happens to be zeros, so we don't really see any difference between F transpose and F. Moreover, F transpose is 4 by 4, it's a square matrix. F is also a 4 by 4 square matrix. We see something similar with the identity matrix. The example has specifically I3, it's a 3 by 3 identity. The identity matrix has 1s along the main diagonal and zeros everywhere else. The transpose of this identity is the same thing, 1s along the main diagonal and zeros everywhere else. I is 3 by 3 and I transpose is also 3 by 3. Let's try to transpose matrix G. The first column, 1, 4, 5, becomes the first row, 1, 4, 5. The second column, 4, 2, 6, becomes the second row, 4, 2, 6. The third column, 5, 6, 3, becomes the third row, 5, 6, 3. Interestingly, G and G transpose look the same. This is because G is a symmetric matrix. Even though we did switch to rows and columns, or if we want to think about the other way, as flipping the 4, 5, 6 across the main diagonal, the issue is that we flip 4, 5, 6 one way, we also flip the 4, 5, 6 the other way. So we really don't see anything different between G and G transpose. To summarize, when we transpose a matrix, we switch the rows and the columns, and therefore the dimensions of the matrix may also change. In the case of a square matrix, since the row and column dimensions are the same, the dimensions do not change when we transpose. When we transpose a matrix that is symmetric or diagonal, we don't see any effect. The identity matrix is a specific example of a diagonal matrix, with ones along the main diagonal. When we add and subtract two matrices, we add and subtract element by element, which means we cannot add and subtract matrices that have different dimensions. Scalar multiplication is when we multiply a number to the entire matrix. Each element of the matrix is multiplied by that number. But matrix multiplication is much tougher. The elements in the row of the left matrix is multiplied element by element with the elements in the column of the right matrix, and then we add together all those products. It's quite confusing. The example will hopefully make much more sense of matrix multiplication. It's really important to keep in mind that the number of columns in the left matrix must match the number of rows in the right matrix. Otherwise, matrix multiplication does not exist. It's undefined. It doesn't work. I like to think of it as the inside dimensions of the matrix have to be the same in order for the matrices to multiply. And the product of these two matrices that have multiplied together will have the outside dimensions of the matrices that gave rise to the product. I don't know how official these terminologies are, inside dimension, outside dimension, but it works for me. It's how I think about matrix multiplication. The identity matrix is a matrix form of a 1. You know how if we multiply something by 1 we get back the original thing? This is the matrix form of that. The symbol for identity matrix is I, and sometimes there's a subscript n that tells you the dimension. For example, I2 looks like 1001, it's a 2 by 2 identity. I3 is a 3 by 3 identity, I4 is a 4 by 4 identity, and so on. For all of these identity matrices, we have ones along the main diagonal and zeros everywhere else, and it's always a square matrix. A really important thing to keep in mind about multiplying matrices is that the order of multiplication matters. If we multiply matrix A with matrix B, it may not be the same as multiplying matrix B with matrix A. Although this order doesn't really matter when we multiply with the identity. For example, if we go matrix A multiplied by the identity, or identity multiplied by matrix A. Since the identity is like the matrix equivalent of a 1, we get back the original matrix that was multiplied to the identity. We can also exponentiate a matrix, or raise a matrix to a power. We just multiply that many number of matrices together to raise it to that power. Let's take a look at this huge example that will summarize everything that we have seen in this lesson. Matrix A plus matrix B. We add element by element. 2 plus negative 3 is negative 1. 0 plus 7 is 7. Negative 2 plus 0 is negative 2. 3 plus 1 is 4. Negative 1 plus negative 1 is negative 2. 5 plus 2 is 7. Matrix A times matrix B. The first thing I look at is their dimensions. Matrix A is 2 by 3, 2 rows and 3 columns. Matrix B is also 2 by 3. There's a problem here. This inside dimension, the 3 and 2, they're not the same, and so these two matrices cannot multiply. A times B is undefined. The proper way of saying this is the number of columns of the left matrix doesn't match the number of rows of the right matrix, and therefore these matrices have incompatible dimensions for matrix multiplication. A plus C is undefined because we can't add element by element. We would have too many elements or too few elements. We can just add some of these and see what happens. 2 plus 0 is 0. 0 plus negative 5 is negative 5. Negative 2 plus, we ran out of elements. Since A and C have different dimensions, we cannot add or subtract these two matrices together. A transpose plus C. I just do this sequentially. A is that, then take the transpose of it. The first row, 2, 0, negative 2, becomes the first column. The second row, 3, negative 1, 5, becomes the second column. And we add to C, element by element. 2 plus 0 is 2, 3 plus negative 5 is negative 2, and so on. A transpose plus C, the whole thing transpose. It's important to keep in mind those brackets. Just like in regular normal algebra, we have to take into account bedmass, the order of operations. And so we have to deal with the stuff in the brackets first, the A transpose plus C, before taking the transpose of the sum. A transpose plus C, we got that from part D, and then take the transpose of it. The column 2, 4, negative 3 becomes a row 2, 4, negative 3. The column negative 2, 0, 7 becomes the row negative 2, 0, 7. A times C. A is 2 by 3, and C is 3 by 2. So yes, in fact, these two inner dimensions match, and therefore we can multiply these two matrices together. Now watch carefully, matrix multiplication is quite challenging. It's easy for me to mess up. We take the row of the left matrix, 2, 0, negative 2, and multiply element by element with the column in the right matrix, the 0, 4, negative 1. 2 times 0 is 0, 0 times 4 is 0, negative 2 times negative 1 is a positive 2. Add them all together, that entry, the 2, came from multiplying the first row in the first column, so then the 2 is going to go into the first row, first column of the product matrix. Then we take that 2, 0, negative 2 again and multiply with the second column of C. 2 times negative 5 is negative 10, 0 times 1 is 0, negative 2 times 2 is negative 4. Add them all together, we have negative 14. And we put that in the first row, second column of the product matrix because it came from multiplying together the first row with the second column. Next we deal with the second row of A. 3, negative 1, 5. We multiply that with the first column of C. 0, 4, negative 1. 3 times 0 is 0. Negative 1 times 4 is negative 4. 5 times negative 1 is negative 5. Add them all together, we have negative 9. In the second row, first column, because it came from multiplying the second row of A with the first column of C. And now we multiply that 3, 1, negative 5 with the second column of C. 3 times negative 5 is negative 15. Negative 1 times 1 is negative 1, and 5 times 2 is 10. Add them all together, we have negative 6. That came from multiplying the second row of A with the second column. So negative 6 goes into second row, second column in the product matrix. It's no coincidence that the product is 2 by 2. The product dimensions comes from the outer dimensions of the two matrices that gave rise to it. In this case, A is 2 by 3 and C is 3 by 2. So these two, the inner dimensions 3, they match up. We can multiply these two and the product is going to be the outer dimensions 2 by 2. C times I, we're going to multiply matrix C, which is 3 by 2, with the identity. But what identity do we use? It has to be the identity that is compatible with multiplying to the right of C. So since C is 3 by 2, we need the inner dimensions to match. So then the identity has to be 2 by 2. Now knowing that we have I2, C multiplying with identity, we're going to get C back. 2I minus D. D is a 2 by 2 matrix. So then I also needs to be 2 by 2 in order for subtraction and also addition to be defined. 2I, we multiply all the elements of the identity by 2 and then subtract D, element by element. 2 minus 1 is 1, 0 minus 2 is negative 2, 0 minus 0 is 0, 2 minus negative 1 is 3. 3b minus half ct. First, let's figure out what is 3b. Take the matrix B and multiply all of the entries by 3. And then half C transpose. We can do this two ways. The first way is taking the transpose of C and then multiplying by half. Or we can multiply C by half and then taking the transpose. The order doesn't matter in this case with scalar multiplication and taking the transpose. So in this case, the solution happens to take the transpose first. After taking a transpose, then multiplying by that half scalar. And we can subtract element by element. This question is tough because there are fractions that we will be subtracting. Negative 9 minus 0 is negative 9. 21 minus 2 is 19. 0 subtract negative half is a positive half. 3, subtract a -5/2. Remember common denominators for adding and subtracting fractions? We have to turn that 3 into a something over 2. In this case, we have a 3/1, so multiply numerator and denominator by 2. We have 6/2. So 6 minus a -5 is 11/2. -3 minus a half. Think of this -3/1 as -6/2. -6 minus a 1 is a -7/2. 6 minus 1 is 5. AC squared. We calculated from part F that AC is 2, -14, -9, -6. The squared tells us to multiply two of these ACs together. 2 and -14. We multiply that row with the column 2, -9. 2 times 2, and then -14 times -9. Add everything together, it's 130. We put 130 in the first row, first column, because it came from multiplying the first row of the left matrix with the first column of the right matrix. Then take the same row, 2, -14, in the left matrix, and multiply by the column -14, -6 of the right matrix. 2 times -14 plus -14 times -6. Add them together, it's 56. We put 56 in the first row, second column, because it came from multiplying the first row of the left matrix with the second column of the right matrix. Then we take the second row of the left matrix, -9, -6, multiply with the first column of the right matrix. -9 times 2, then -6 times -9. Add those products together, we have 36. And 36 goes into the second row, first column. Then take the same row in the left matrix and multiply by the second column in the right matrix. -9 times -14, -6 times -6. Add those together, we have 162. 162 goes into the second row, second column. D cubed. Have 3 of these d's multiplied together. Do them sequentially. The 1, 2 multiplied by 1, 0, we get 1. 1, 2 multiplied by 2, -1, that gives 0. 0, -1 multiplied by 1, 0, we get 0. 0, -1 multiplied by 2, -1, we get 1. And then that matrix, which is d squared, we multiply on another d. 1 and 0 multiply to that 1, 0. 1, 0 multiply to 2, -1. And 0, 1 multiply to 1, 0. And 0, 1 multiply to 2, -1. We get 1, 2, 0, -1. A faster way of thinking about this is realizing that, hey, that 1, 0, 0, 1, that's the identity. If we multiply a matrix by the identity, we get the matrix back. D squared being the identity, we multiply another d, we just get d back. Matrix division, don't do it. There's no such thing. We can divide by a scalar. It's not really division by a scalar. Think of it as multiplying by a reciprocal. If we were to divide matrix A by 2, it's probably not the best idea to write that as A divided by 2. Write it as half A. If we want to divide A by 3, rewrite that as 1/3 times A. It's a reciprocal. If we were to divide a matrix by -5, write it as -1/5 multiplied by that matrix. Matrix division, like dividing two matrices together, also does not exist. Instead, we have to multiply by the inverse. And it just so happens that when we multiply a matrix by its inverse, we get the identity, and the order of multiplication doesn't matter. So we can multiply A with A inverse. That's what that -1 means. It's not division, it's inverse. That's equal to, if we put the inverse to the left of A and then multiplying A. In either of those two cases, we get the identity.